Hi everyone, today we will be learning linear regression with linear algebra, and we will be doing this by the lectures of Purdue University, and the link is also included in artificialturk.com. And this video is recorded for the YouTube channel Makine Öğrenmesi, and you can learn linear regression with linear algebra from this post, and this video is a better explanation for the codes, and we will play with some parameters to observe and analyze linear regression deeply. We will be doing this by Python and also the libraries NumPy and Matplotlib for graphing. And let's begin. Well, linear regression is a very simple idea. It has a very simple idea, and it's the simple machine learning model. And probably you are searching for linear regression models. You are searching for machine learning algorithms, and you are searching for linear regression because it's easy, and it's also the first algorithm that you see in all courses, in all tutorials, and you probably see some explanations like that. So these explanations include matrices, and there are some matrix multiplications. There are some strange notations. It may be strange to you, and it was also strange for me for a long time. But you're probably looking for linear regression, especially if you are trying to learn neural networks. You're probably looking for the gradient descent solution of it, and we will be also posting it on artificialturk.com. We will be discussing the gradient descent solution, but this solution is about the linear algebra solution of it. So both solution includes the same idea. You have the same formula, you have the same loss function. However, the way that they get the right parameters for models are different, because in linear algebra solution you get the optimized solution at one step, but it has drawbacks, and also with gradient descent you are getting the solution by maybe thousands of steps. It has also some drawbacks and benefits. We will be discussing these, and the video is recorded for switching some parameters. We will be doing this, and let's go to the topic. Well, in real life we have some data, and probably our inputs are related to output. And we are applying machine learning models to observe the relationship between input and output, and also this can be explained by the kilometer per hour, or your speed can be your input, and the output is probably the gasoline consumption. So if you are driving with high speed, your car will consume more, and you want to predict it, and you want to fit a line on it. You want to fit a line on your data, and it means that you want a good parameters for best fitting line. Before going to the math solution of it, let's review our knowledge about the line. So line consists of two parameters. This is m and b, and these are for approaching your input to the output. So m corresponds to the slope of the line, and b is the intercept parameter. So if your b is 1, and also if your slope is larger than 1, this is what you observe. And this explanation is from the mathsfun.com, and you can learn about it. Well, we have the data. It can be a kilometer per hour and the gasoline consumption, or it can be the area of the house and the price of it. And it can be anything that has a linear relationship, but in real life the linear relationship is not always observed. So we have uh, machine learning algorithms other than that for other data sets, and for this problem we will be creating a data set that has a linear relationship, and also we will be doing the same optimization same linear algebra solution for the different data sets. So one way to solve it is it requires linear algebra. Before going to that, let's import our libraries. NumPy is for the mathematical operations, Matplot for the graphing, and we will be importing NumPy linear algebra to inverse the matrix, and also we will be adding random state to have the same solution with you. So to create a dataset, we first define x that is from 1 to 100, and with that we will be having from 0 to 99 elements, and also our formula is mx plus b. So let's define a dataset like that, and we will add some randomness on it. So to do that, let's say that we have y, and let's go with the same principle, 2x plus 1. This means that our m is 2, our intercept is 1, and if we want to graph it, we will say that plt.scatter x and y, plt.shove, and when we run it we will be observing a line, nearly a line, because it has some emptiness between the points, because we scatter it. So for the 38 value we have 77. It is because if you multiply 38 by 2 and if you add 1 on it, you have 77. So in this data we have no randomness, and we can predict all the points in the data set. So, but in real life we have randomness in our data because the life has randomness. So if you take the data set of a gasoline consumption according to your speed, you will end up with the data that doesn't have exact linear relationship between input and output. So to add a randomness on it, we say that numpy random normal, and let's take it from here, numpy random normal, and this is actually the standard normal distribution random number generator. And if you are not familiar with it, you can just assume that we are adding random values that has a mean of 0, and our random values are nearly between -1 and 1, and also we will be creating 100 of random dataset, and when we run it we see that there are some randomness on our data. So we can increase this randomness by increasing the standard deviation, or we can multiply it from here, and this will result in an awkward data set. However, you get the point. We can increase the randomness by adding some standard deviation of it, or changing the standard deviation of it, and this 3 multiplied by the standard normal distribution with standard deviation 10 means that standard deviation with 30. So the dataset is nearly similar, and you get the idea. So let's be honest with the post. So we have a random data like that. Also, I would like to change the standard deviation. Let's observe it again. So this looks good. So we add a randomness of it. So and we can say that it has a linear relationship, so we can fit a line on it and we can predict some value for our machine learning algorithm. And also it looks like a real world data now. So now let's go to the math part of it. So the y is our output, and our input is b1x plus b0 plus epsilon. So you say that what is this kind of symbols? So it means that b1 is our m, so it is changed like that. b0 is our b, the intercept, and also we have some epsilon parameter here. So this stands for what? Let's explain it on here. Let's say that we have a value like that. We have dataset like that, and I'm saying that print the first value of y. Say, and let's make it equal to the 2 multiplied by the first value of 0 plus the first value of plus 1, and also let's take this randomness and say that this is the random, or epsilon, let's say it epsilon is equal to this, and plus the first parameter of the epsilon. So let's run it again and see what we have. And we have some problem here. Yes. I hate it. So with epsilon, the left side and the right side must be equal. So the formula includes epsilon, the random parameter, because we need to say that this is exactly equal. So we say that there is a randomness in our data set, and this randomness is already determined by the random vector. And when we run it, we will see that minus 11 is not equal to 1, but minus 11 is equal to minus 11 minus 11. So the epsilon is for that. So the epsilon includes the randomness to our problem, to our data set. So this is why the notation is like that. So let's get back to the our mathematical part, and this is our formula, and this is the epsilon is for saying that the left side is equal to the right hand side, and we have actually y1 is equal to b0 plus b1x1 plus epsilon 1, y2 is equal to b0 plus b1x2 plus epsilon 2. So this is the actually the same thing with this code here. So these are the same. So why don't we vectorize this matrix form? So we have some y's here from 1 to n, and we have some x to n here. So this says that b0 is b1 plus b1 multiplied by x1, and add randomness parameter on it. So it means that y1 is equal to b0 plus b1x1 plus epsilon 1. y2 is equal to b0 plus b1x2 plus epsilon 2. So it goes like that. And so let's split our b0 and b1 to another matrix and multiply it like that. y1 is equal to 1 multiplied by b0 plus x1 multiplied by b1 and plus epsilon 1. y2 is equal to 1 multiplied by b0, x2 multiplied by b1 plus epsilon 2. yn is equal to 1 multiplied by b0, xn multiplied by b1 plus en, epsilon n. So y is our output, b1 is our m, b0 is our b intercept, and so the last two images represent the same equation. Actually, these three equation set is equal to the same. They are equal to each other. So we want to find such a B matrix. We will call it B matrix, that makes X multiplied by B as close as possible to Y matrix. So in optimization, we have Y is equal to X beta plus epsilon. So we want epsilon is equal to the Y minus XB. So if we do not have right values of V, such that before going to that we need to do something. But if we do not have the right values of beta, it means that we do not have a good value of m and b, or b1 and b0. We will have different errors. So if they are equal, if left hand side and right hand side is equal to each other, if you subtract the right hand side from the left hand side, it should be equal to the 0, right? But we have randomness on our data set, so we need to minimize the error. So epsilon, we call it randomness, but it can be said that it's also stands for the error. So our error is y minus x multiplied by beta, and it should be 0, and we need to minimize it as fast as we can. And instead of above, we want to minimize y minus x beta squared. So this stands for the residual sum of squares, and the square part of it is for avoiding getting wrong error by the sign of the data actually. So because if you have a some linear regression equation and you fit a line and you try to find the error, if let's go back to the post. If you would like to subtract the true value, real value from the predicted value, you will end up with, for this, the real value is let's say 58, and the predicted value is 60. So you get -2 if you do not square. And you go here, you are trying to subtract the real value from the predicted value. You have 70 in the true value, and you have 64 for the predicted value. And if you subtract the real value from the predicted value, you will end up with 6. So this is not a standard way. So this is not a ethical way to approach the errors. So we are squaring it. So the -2 becomes 4, 6 becomes 36. So we do not care about the signs. We do not care about the minuses. So this is what it stands. This is what the square stands in here. So we can penalize the errors regardless of the sign of the y minus x multiplied by beta, and also the derivative. So we will get the derivative with respect to beta, and we will make it equal to the 0. So there are some linear algebra part of it. There are some linear algebra optimization. So I do not want to confuse you, but the idea is the same with the differentiation. So you will end up with x transpose y is equal to x transpose x beta. So you need to also actually you get these equations, and then you get back here. So you can throw the -2 because it doesn't have importance on getting the right value of beta. So when you set the derivative to the 0, you will end up with x transpose x inverse x transpose y. So this is the true value of the betas. So beta matrix means that we have b0 and b1, and if we optimize it, we will end up with the best value of b0 and b1. So how will we compare it? So when we prepare our data set, we have m and b parameters that are designed by us. So we need to have similar values, close values to these values. Because we add the randomness of it, it will not be exactly 2 and 1, but it will be near to these points. So you see that when we convert it, when we try to get B matrix, we add a one column here. So to do that, we will stack the ones to the left side of our X data set. So let's do it. So let's say that stack the ones to the left side of our X. When we print it, we will observe. So you see that the ones are included in the left side of our data set, and so we need to get y's from here. So to get y, we need to multiply the X matrix with B matrix, and also we need to add it to the randomness. So we will do it like that. So this is the our y values, because it says that x multiplied by 1 and 2, it says that it is transpose because 1 and 2 are in the matrix of the shape of 2 and 1. So we have 102 matrix for x and 2 1 matrix for beta, and the result is 101. So we need to add the randomness 101, and after that we have the y's, and also to optimize it we will be applying this formula. So the transpose is x dot transpose or x dot t, and the inverse is linear algebra dot inverse. And if you are familiar with NumPy, this formula is the exact value of this formula. So we have this, and we will be seeing the right parameters. Let's delete it. So we have the optimized value of beta 0 and beta 1. So let's graph it. Let's do it on here, and also we can say that we are looking for all values of x, but for the second column. So we are graphing this, so this is why it's written like that. And also we want to plot a line that says that get the second column of the x matrix and also multiply it by the beta value. It means that we are doing the same thing here. So we are doing this part of our multiplication. So not the randomness here, because in linear regression we cannot predict the randomness. So we can predict the relationship between two values. So when we run it, we are seeing that our line is perfectly fitted on our data set, and we are done. But let's play with some parameters, and let's say that the standard deviation is higher than that, and let's say that the standard deviation is we do not have to multiply. We just say that let's say that it's 30. So you see that it predicts, but the line predicts, but it's not accurate. And this is about the randomness of the dataset. And when you increase it more and more, you will have some solution, but it will be unimportant to have parameters. But before going to that, let's make it smaller again, and let's observe that we predetermined the parameters of the linear regression like 2 and 1. So m is 2, b is 1. It means that intercept is 1 and slope is 2. It says that b1 is 2, b0 is 1. So we need to get the closed values. When we apply it, the true values of b1 and b2 is 2 and 0.88. So it's nearly close to the predetermined values. However, if you decrease the standard deviation, it will be closer and closer, 2 and 1. And also, if you decrease the standard deviation of the randomness, you will get even more closer, 2 and 1. But if you increase it, it will be, you see that the slope is not largely affected, but the intercept is largely affected. So this is what we observe from the linear regression. And also, before going to that, you can see some posts on here, and also we have I have some courses on YouTube. So it says that beyond MNIST example practical convolutional neural network course. So you can also find writings on the lectures of this course in this website, and also in here we'll be talking about Keras, image augmentation, and the practical side of convolutional neural networks, so you can check it also. Thanks for listening.